This is how Mosky is actually built. 3 pieces: a page you type into, a Python process that answers, and a language model on a graphics card. Everything else is plumbing between those 3. Start with the shape because it explains every decision after it. There is no React app, no database, no message queue, and no cloud. There is a browser tab, one Python process on this machine, and a llama.cpp server holding the model. The tab and the process talk over plain HTTP. The process and the model talk over the OpenAI chat format. That is the whole architecture. There are 2 front ends, and this is the part worth understanding. One is the terminal, you type Mosky and get a REPL. The other is the web app on port 8095, which is what your phone and the desktop window use. They are not 2 products. The web server does not re-implement the agent loop. It imports the same agent class the terminal uses, with the same tools, the same permission rules, the same memory. The website only adds a headless user interface and keeps 1 agent per conversation. The front end itself is 1 file, 1116 lines of plain HTML, CSS, and JavaScript, living as a string inside server.py and handed out whole when you load the page. No NPM, no bundler, no build step, nothing to compile. It is a progressive web app, so it installs to the phone home screen, and it keeps your session ID, your token, and your theme in local storage. The service worker is deliberately a pass-through. Caching and assistant answers would be wrong. Between them is the wire, 23 HTTP routes on a FastAPI app. The ones that matter are ask for a whole answer and ask/stream, which sends the reply back token by token over server-sent events. Then speech to text, text to speech, sessions, history, projects, uploads, and a cancel route so you can stop a turn that is running. Every one of them checks a bearer token, and the server refuses to bind to anything but loopback unless that token is set, because this endpoint runs shell commands. On the back end, there is a single Python process. It keeps 1 agent object per conversation, so your chat about the CRM does not contaminate your chat about the truck, and it serializes requests. The llama.cpp server has 1 slot, so asking it to run 2 turns at once does not make anything faster, it just makes both of them worse. If a conversation is already busy, the server says so with a 409 instead of queuing silently. Underneath that is the agent loop, and honestly the loop is the product. Send the conversation to the model. If it asks for tools, run them, put the results back in the conversation, and send it again. Repeat until it answers in words instead of tool calls, up to 40 steps in 1 turn. 2 details make it survive a small model. Tool errors come back as text rather than exceptions, so a malformed call teaches it to correct itself instead of killing the session. And at 75% of the window, older turns get summarized, never splitting a tool call from its result, which is the usual way a naive compactor breaks an agent. The model is QN 3.8, 27 billion parameters, quantized to about 13 gigabytes and served by llama.cpp. Here is the part people get wrong. Mosky talks to 127.0.0.1, port 8090, exactly as it always did, but nothing is running there anymore. That port is a systemd socket proxy to the Dell, which now holds both graphics cards. The harness never had to know. The window is 28,672 tokens, and Mosky reads that number off the server at startup rather than trusting its own config. Tools come in 3 rings. The inner ring is carried on every message. 8 file and shell tools, 3 memory tools, 2 for skills, 1 for delegating to a subagent. The second ring only exists in the web app, 17 of them. Gmail drafting, browser control, Twilio queries, notes, and consult, which hands a hard question to Claude Opus and returns the answer inline. The third ring is the shelf. 29 more tools sitting in JSON files on your desktop, not in his head, until he calls enable tools and picks the group up. That is 61 reachable, for the context cost of about 15. The shelf is model context protocol servers. Two of them are local programs Mosky starts and talks to over a pipe. One of them, the CRM, is a Supabase edge function out on the internet, reached over HTTPS. Both speak the same JSON RPC protocol, so the handshake, the tool listing and the call formatting are written once in a base class, and each transport only supplies open, request, and notify. Their credentials never touch a config file. Settings holds a $brace placeholder, and the launcher fills it from the vault at start. There is no database in this system at all. Conversations are JSON files under .mosky/sessions. Projects are a folder with a meta file and whatever you uploaded. The memory vault is the same 1 fact per file markdown Claude Code writes, read with search tools rather than inlined, because the vault is roughly 100,000 tokens against a 28,000 token window. And the tool schemas sit on your desktop as JSON you can open. All of it is inspectable, editable, and deletable with a text editor. Voice is the same pipeline with 2 extra hops. The browser records you and posts the audio to the server, which forwards it to Whisper and hands back text. The text goes through the ordinary loop. The answer is split into sentences, and each one is spoken by Kokoro, running in the server process on the graphics card. Both are proxied rather than called from the phone directly. One origin, one token, and Whisper can move machines without the client noticing. The white and blue orb on screen is doing exactly one job, telling you which of those stages you are in. So here is one turn all the way through. You type. The page posts to ask/stream with your token. The server finds your conversation, takes its lock, and hands the text to the agent. The agent builds a system prompt, checks whether the context needs compacting, and calls llama.cpp, which is really the DEL. Tokens come back as they are generated. If the model asks for a tool, the harness runs it through permissions and hooks and feeds the result back. When the answer is finally words, it streams to your screen. The session is written to disk, and the lock is released. One last thing. Nothing in this deck came from memory. The test suite was run. 176 tests, all passing in 9 seconds with no model server needed. The line counts were counted. The route count came from the decorators. The context window was read off llama.cpp's own props in point, and the socket proxy was confirmed listening and 18 hours up. If a figure is on a slide, something on this machine was asked for it.